Welcome. Today we'll be discussing how we can use counters for random sequences of binary numbers. My name is SP. Let's dive straight into it. This video's objective is to help you understand how different flip-flops can be used to create counters with random binary sequences. We will also try solving some questions to understand different possible cases for creating counters for the same random sequences. We will first go through some prerequisite required for this lesson. Then we will directly dive into the procedure for solving related questions. Okay, so let's go through some basic definitions. What is a counter? A counter is a device which stores and sometimes displays the number of times a particular event or process has occurred, often in relationship to a clock signal. How do decade counters work? The basic decade counter is an electronic circuit with a 4-bit binary output and a input signal. What is a binary counter? Binary counters are circuits that generate binary sequences that can be associated with the number of clock signal pulses applied to the input. Okay, so now we discuss the steps to design a binary counter. The first step to design a binary counter is we first have to jot down the given sequence with its present state and next state. The next step, we have to use the excitation table of the flip-flop we are using to design the counter and write down the table of respective flip-flop. Once you have written down the excitation table, you have to compare the present state and next state to the result with reference to our excitation table. The third step is that we have to solve the given inputs using K-maps with the present state variables. Lastly, we write down the circuit according to the calculated inputs. Now, the following are the steps to design a counter with random binary sequences. The first step is to find out how many flip-flops are required. Second, draw the state diagram. Third, write the excitation table for respective flip-flop. Fourth, write the present and the next state table. And the last, write the K-maps for the inputs. I will discuss more about the above steps in the upcoming slides. Now moving to the core part of the lesson. The first step is to decide the number of flip-flops that we require. Let us assume we have a mod 8 counter. So we can use the formula 2 to the power n is greater than equal to n, where 2 to the power small n is greater than equal to 8. Therefore, n is equal to 3. Or we also have a formula in presence of a scientific calculator, we can use the log n base 2, where n is the number of states in a counter. Moving on, let's assume we have the following binary numbers given to us: 000, 100, 111, 010, 011, and 000. The state diagram for these is something like this, where 000 is 0, 010 is 4, 111 is 7, 100 is 2, and 011 is 3. In our third step, we have to write the excitation table of the respective flip-flop. So in our case, we will be assuming a T flip-flop. Therefore, the excitation table for a T flip-flop is where Q1 is the present state, Q1 plus 1 is the next state. We have 0, 0, 0, 1, 1, 0, 1, 1. And the results are T where it is 0, 1, 1, 0. We actually have to remember this in order to solve the question. Moving to the fourth and the most complex step of the process, we have to write the present state and next state table. Using the given excitation table for the T flip-flop, we have to fill the input column. Over here we have already filled it, but I'll explain how it's done. So over here we have the present state column with QA, QB, QC, and the next state column with QA1, QA, QA plus 1, QB plus 1, and QC plus 1. We have the 8 midterms on the left, to which we write their binaries in the present state column. So we have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, and so on. The next state column is where we write the next state that we observed in our state diagram. Coming back to this, we had observed that the next state of 4 was 0, for 7 it was 2, for 2 it was 3, and for 3 the next state was 0. Remembering this sequence, we fill out the next state column. So for 0, 0, 0, which was 0, we write the fourth minterm, which is 1, 0, 0. For 1, as we observed, there was no 1 in our state diagram, so we will put the don't care condition. For 2, we had 3, so we put 0, 1, 1. For 3, we had 0 in the last case, so we put 0, 0, 0. But for 4, we had 7. As the seventh present state is 1, 1, 1, that is what we put over here, and we get 1, 1, 1. Now for 5 and 6, they weren't there in the state diagram, so we directly put don't care for the next state and the input column, and we forget about them for now. For 7, it was 2. The present state for 2 is 0, 1, 0, which we write down in the next state column, and we are done with that part. Moving on, now we have to compare the columns in the present state and the next state with respect to our excitation table, which we saw previously over here. We have to remember that 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, and 1, 1 is 0. Remembering this table, we will move on to compare each column with its corresponding next state. We start with QA and QA plus 1. So 0, 1 will be 1. 0x, as is don't care, we put don't care. 0, 0 is 0, 0, 0 is 0, 1, 1 is also 0. We again have don't cares over here, so those are carried by themselves. Next, we have 1, 0, which becomes 1. For QB, we have 0, 0, so 0, again I don't care, so we leave it as it is. Next, for 2, we have 1 and 1, so we get a 0, 1 and 0, we get a 1, 0 and 1, we get a 1, then 2 don't care, leave them as it is. Moving to the last minterm 7, we get 1 and 1, which is also 0. Now coming to the last and third column over here, we have QC, we compare to QC plus 1. 0, 0 becomes 0, don't care, leave it as it is. 0 and 1, we get 1, 1 and 0, we get 1, 0, 1, again we get 1, 2 don't care conditions, leave them as it is, and the last is 1 and 0, which is 1. Now we have completed the input column. With TA, TP and TC, we'll be using this in our final step. Moving on, now move to the last step and the easiest step, step number 5. We have to write down the K maps for TA, TB and TC, which are the inputs in our previous step. Now K map for TA is this. I have already filled the values that we have taken from each column TA, TB and TC, and we'll pair them. We have two pairs here, and this is the equation we get. Moving on, K map for TB is this, and we get one pair here and one pair here. Finally, we get this equation. TB is equal to QA dash QC plus QA QB dash. The last K map is for TC, and we get two quads over here, giving us the last and final equation. TC is equal to QA plus QB. With this, we come to an end to this presentation. Thank you so much.